All right, and we're back. So week two. Week two of that course really just focused on covering um linear regression with multiple variables. So the first thing that we started to look at really is that topic specifically with, you know, what happens when you have multiple different features, like, say hundreds of features, or in this case, I think the common example used has like house prices with, or house price prediction with maybe um like 4 to 6 features. If we go through, looks something like this. Realistically, this doesn't really differ very much from what we've seen previously. You just increase the number of thetas, um, and specifically it looks something like this, right? So again, you're going to have your um, theta naught, which is, your intercept, your theta 1, your theta 2, all the way up to your theta n. This can go on up to, near infinity. Not that it should go up to near infinity, but it can. So realistically, this doesn't have too much of an effect on your linear regression equation. Um, you just have to scale up. So now, well, previously where you're doing, you're solving for theta 1, you'll now also be solving for all the other thetas. Um, and Andrew doesn't cover it now, but later on when he sort of covers vectorization and stuff like that, um, you see that when you put this all into a vector, it's actually not too difficult to do. But this is just some of the math around it. And this is sort of what I was talking about. So for each theta, well, for each next theta, theta j that is, so the parameter that you're looking at, that's going to be equal to the current theta j minus your learning rate times the partial derivative of your cost function, which is what you've seen previously, with respect to that theta j. So basically, you're just seeing how much of a contribution that theta j has had to the cost function, and you scale it back by that certain amount. And here, really, this is just showing the same thing, but more explicitly. So, for theta naught, it's this, theta 1, it's this, theta 2, it's this. You'll sort of see that it's pretty similar to what you would have had previously. You have your theta 1, it's going to be equal to theta 1 minus your learning rate times the partial derivative of the cost function with respect to theta 1, or rather with respect to theta, which we looked at previously, but now it's just with respect to theta 1, with respect to theta 2, etc. And this is actually quite simple, so it normally just ends up being, this part here is, oh, sorry, I see my screen's blocking this video game. You have your partial derivative here. The only thing that really changes ultimately is, this here, which is like, which is the previous or the current value of x1, the current value of x2, the current value of x0, which corresponds to the parameter theta 0, theta 1, and theta 2. So the next thing that Andrew sort of covers is this idea of feature scaling, which is quite important once you get multiple features of different scale, especially with our current implementation of gradient descent, which doesn't really take into account this. Later versions do. They sort of keep track of, different scales and maybe adjust depending on, what figures each different dimension sort of expects. So what happens here is, if you get, say, something like this, where x1 ranges in size between 0 to 2000 and x2 being, say, the number of bedrooms for a house, x1 being the size of the house, x2 being the number of bedrooms, being 1 to 5, then what happens is some features will learn much faster and some features will learn much slower. So say, for example, this x1 is likely to learn a bit slower because, the 0 to 2000 is just so much more distance to cover. And when you have sort of some features being fast scaling and some features being slow scaling, then your learning curve sort of looks a bit weird and it doesn't work as well or as quickly as it could. So what you realistically want is you want something like this. These lines here are indicating the contours of the gradient, so uh, each line sort of indicates the same value, similar to a map contour. But you want it something like this. And this is a simplified 2D version, but you want it to be very roughly similar in scale. And there's one way to really accomplish this, which is mean normalization. And this is quite a simple concept. Essentially, what you're going to do is you want to subtract every single value in your in one dimension by the average of that dimension, the mean. And what this will do is it will make it so that essentially the mean is 0. So everything's going to be centered on 0. And then you're going to divide that either by the range of the values or the standard deviation of the values. I prefer standard deviation because sometimes if you have values that say spike, so like let's say normally your values actually lie between like negative 100 to 100. Sometimes you might get a value that is say like 600, and then all of a sudden, because of the 600 value, your values are going to be stuck in this sort of like 0. I don't know, 0.1 to negative 0.1 range. Not that, probably like 0.15. Um, so this is sort of covered here. Like realistically, it doesn't matter too much what range of values like these end up in, but normally you want it between -1 and 1. But it doesn't have to be that. It can be between negative 0.5 and 0.5, or it can be between say -3 and 3. It's perfectly fine. You just generally want all your values to be, in this similar range. And then up next, Andrew sort of talks a bit about debugging loss curves or cost curves in his case. This is quite common. It's a good skill to have, but it's not really, well, it is something that is taught, but most of the time you'll learn this by sort of looking at a cost curve and sort of trying to gauge what a model is doing and like behind the scenes based on what you're seeing from this cost curve. It's a very powerful debugging tool when you train your own models. But he covers a few cases like here, which is, when you select a learning rate that's a bit too large, it makes your gradient descent updates a bit too eager, and it can actually increase the cost of a function so that as you learn, you're not getting this sort of nice, downward slope, downwards minimization of your cost. You're actually getting an increase in cost, which is quite bad. You can also get this. I don't actually know. I've never seen something like this myself. I don't know in what situation you get something like this, but I guess this is when you pick an alpha where maybe you go down, but then you go back up, and then you go down and you go back up. And that's just because it's overshooting the minimum. Let's see. Does he have any other cases here? Not so much. He's really just talking about the learning rate here. One being, if your alpha is too small, you're going to converge slowly, so it's inefficient. If it's too large, then you'll just get issues. And normally, yep, you're absolutely right. You try your alpha in batches of 10. So, 1, 0.1, 0.001. So, I mean, factors of 10. And you normally start with 1 times 10 to the -3, which is this one here. Or at least that is my experience. So this one here is just like a practical example. But something else which is covered is that, you don't actually, when you do this linear regression or when you do this regression, it's not always the case that you're going to have your x relationship be like standard x linear. It can be a polynomial relationships, or which gives you, I guess, polynomial regression, where you have, like x and then x squared and then x cubed and then x to the power of 4 and so on and so forth. And what that allows you to do is allows you to model sort of um, relationships that are a bit more complex, like lines that aren't just straight, for example. And you'll start getting curves and stuff like that. And most of the time, this is what you have. It's not going to be a straight line. Uh, it's going to have a curve, and it's going to have, these non-linearities, which are really quite important. And just briefly touches on the fact that feature scaling is super important here, because if you have, say, normal regression, say the value of the size of the house can range between 1 to 1,000, but suddenly if you go size squared, it goes 1 to 1 million, and size cubed, 1 to a billion. So realistically, that feature scaling is something that you definitely should be doing, um, except for the very simplest of linear regression models. The thing that it covers next, the normal equation, was something that I'd actually completely forgotten about. This is actually a really interesting sort of um, solving method, which makes complete sense, but the thing is that it's only really applicable for simple linear regression models. And the reason for that is because when you get to complex neural networks, or when you get to cases where you have, a lot of features, um, this becomes both impractical from a sort of calculation perspective, and also from basically just an equation perspective. It doesn't really work out. But so what you can do when you have these simple linear regression models is you can basically go and derive it and say, well, we know that we're trying to minimize this sort of gradient descent curve. And what we're really trying to do is we're trying to get to a point where it's at the very bottom of the curve. And if you sort of remember back to basic differentials, I think when you're solving differentials, for an x squared, you're at the bottom when the differential is equal to 0. And so in this case, if you apply that to linear regression, when you get your differential equal to 0, you're at, well, either a local minima or a global minima. This is actually really important, because if you set your derivative to 0, you can calculate the optimal set of parameters, basically, without having to go through the iterative steps. And this is written out a bit more explicitly. So when you have that partial derivative equal to 0, you're at the very bottom of the curve. So basically, set 0 for every parameter that you have, and then you solve for your optimal parameters. And this is sort of the equation for calculating that. Basically a more simplified equation. He doesn't go through the derivation. The derivation I actually went and looked up again just for my own sake, and it's up here. Let me zoom in a bit so it's a bit easier to see. So given a hypothesis function of, theta naught x naught, theta 1 x1, blah blah, up to theta n xn, we want to minimize the least squares cost, which is what we've seen previously, right? J of theta, where xi is the ith sample from a set of m samples. So that is to say, xi is the ith data point from m total data points, and yi is the corresponding expected result. So to proceed, we're going to put this all into matrix notation, such that we have a system of linear equations here. And essentially what that means is we're going to be doing, let's see if I can bring it up, this, where we're stacking it all together. We form a matrix here by putting all these values together like so, and correspondingly we do the same for y, such that the rows match. So This is just an observation here. Each of the input samples is a column vector. Not sure what he means by column vector with n+1 rows here. I'm a little bit confused about the column vector here because normally when you put your data in, each data point corresponds to a row. But in this case, each column is a data point and each row is a feature. But I guess that's just a notation thing. That's how Andrew's done it in his videos. So if we sum up over all the samples, we can go use our matrix notation, which is pretty good. We define something called a design matrix, which is a matrix with m rows, which is what I was sort of talking about here, where each data point is a row, being the ith sample, which is a vector xi transpose. With this, we can rewrite the least squares cost function as following, replacing the explicit sum by matrix multiplication. So for this, this is going to be a bit harder to explain, but essentially, this squared and this summation comes out to be a matrix multiplication. And the way this matrix multiplication works is when you have the transpose of this matrix here, matrix multiplied by itself. Because what happens is normally if you do the square, it's going to be like, if you imagine like two matrices here, you're going to do like that squared, which is essentially that times itself. And then to sum it, you're going to basically go along in the this dimension here. Yeah, I'm not gonna lie, I'm really failing to explain this. But essentially, you'll just have to take my word for it that this is this transpose operation and this matrix multiplication is replacing the summation as well as the square term. So we then simplify this a little bit. Since we're computing a derivative, and that derivative is being set to 0, we throw away this 1/2m part since it's multiplication, and then it turns out that if you sort of multiply this out, we can then simplify it down to this, which then simplifies down to this, which then simplifies down to this. And then if we multiply both sides by x to the inverse, we get the equation which Andrew presented earlier. And this is really good because it's got quite a few, well, it's got a few benefits for simple linear equation cases. You know, for one, you don't need to choose an alpha, you don't need to do an expensive iteration if your data set and your feature size is small. If you had to do, say, feature normalization earlier, you don't have to do it with this because realistically it doesn't matter too much. But on the negative side, you have to compute this term here, which can be quite expensive to compute. I think it's n cubed for the big O notation, which can be quite slow if n is very large. Whereas for gradient descent, you know, even if your n is large, the number of features is large, it doesn't really matter. It just sort of figures it out. But there are situations which you should watch out for where this doesn't work, which is when x transpose times x is non-invertible, and this happens when you have linearly dependent features, which creates redundant features, like this example here, where you can have x1 being the size in feet squared and x2 being the size in meters squared. These two clearly correlate with each other, like they're the exact same thing, it's just a different scale. And the other case is when you have too many features for the amount of data you have. So the example Andrew gives is when your the number of your data points is equal to 10, but say the number of features you have is equal to 100. And the way you sort of deal with this is you either delete some features, use regularization, or you do some sort of dimensionality reduction, which is pretty handy. And that was sort of it for this week. He then goes off and does some Octave. He does an Octave tutorial, which is, I guess, kind of handy. I think the most important part of that tutorial is when he covers vectorization, which I think is this one maybe. Let's see. Here we go, vectorization. And basically, vectorization is when you avoid using loops. So when you program something, say you want to do the summation, normally, you know, if you're quite familiar with programming, or even basically familiar with programming, your first approach will probably just be a loop. But it turns out that if you vectorize this, or you use basically theory around matrices to do this calculation, which is to say, you know, if you do your theta transpose times x to do that summation, it's going to be much quicker. And the reason, well, there's two reasons for it. But I guess the main reason is that you're going to be using a library that's very much optimized. And that leads to the second sort of secondary reason, which is that, you know, that optimized library just doesn't have the overheads of, you know, that for loop. It might be doing something similar in the background, but it's going to be very, very quick in doing it. And then essentially walks through basically a more complicated example where you do this for, you know, the many different parameters example for linear regression. This is pretty helpful, but to be honest, it's not something that you really need to know the derivation of, or you don't. I guess it helps to know the theory, but you don't need to know the theory. You just need to know that it's better to use essentially matrix multiplication from, say, NumPy than to do, you know, a for loop yourself. Pretty straightforward. And that's it for week 2. I think in week 3 he starts covering classification, and also some other things like overfitting, regularization, L1, L2, and then I think the basics of neural networks. So I guess I'll see you guys in that video. Catcha.